Lecture 13. Tensor is a map. Recall that, you see, there's a vector A. Vector A is a first order tensor, which can be expressed by its coordinates and the basis partial of xy. This is invariant, okay? The same vector at P, point P, can be expressed in the dual space by AI dxi. dxi are the basis, are the covector basis, okay, for this space. In partial of xi, you see, remember that this one is the same of this one, you see. There's a lower index because I is in the denominator. So, the vector space TP M3, let's work to the 3-dimensional. This can be extended to the higher dimension. So this is a cotangent space. Now the map, you see, this is the components, okay, on the vector space, act on the components of the tangent, the cotangent space. This leads to, you see, this over here, okay, is the chronic delta, okay, the chronic delta. So, chronic delta ij, you drop j and set I over here, is ai, ai. You see, this ai here is contravariant in this case, this is covariant. This is the same as aj, or ak. You see, because this a dummy index. Okay, let's move now to the second order tensor. Since we are working in Lie derivative applied to the killing vectors, we say applied to the metric to obtain the killing vector, let's recall the map and this second order tensor G bar, you say? So G bar, G double bar, Gij, you see, this here is the basis for the vector space. This here is the basis of the dual space. You see, it is analogous what we did here for the first order tensor, and this is a second order tensor. So I can write at the same point P, this is here is G double bar. G is over here is G double bar, because it is invariant. Now, let's apply the map, okay? Or this here, these are the basis of the tangent vector space. Tensional, and this one is the basis for the dual space. So we'll apply the map here. You see, this is double dot here. You see, then this is attention, this is the inner product, okay? The inner product between partial xy and dxp, okay, it's over here. There's another inner product, okay? This is partial xj, okay, and dxq. So now I can group, okay, this gij, gpq. Now, this is by definition, is the chronic delta, okay? Delta pi. Likewise, this inner product is the chronic delta, delta kj. Now, delta ip, okay, can be applied to gpq, okay? Then this move I over here to the place of P over here. Likewise, delta JK, you see, let's move J here to the in the place. We replace Q by J, and this replace P by I, according to the definition of the Kronecker delta. See? So this one, okay, I obtain Gij. This is lower index with a covariant component. This Ij is contravariant component. Exactly how we derived in, I think, part 1 or part 2. We are in part 5, see? But you just go there and recall all this derivation. So this case, the second order tensor, just to emphasize, this invariant. Okay? So the map is a scalar, the real number. Now it's dummy indices. Okay? I is dummy and J is dummy. So both are dummy indices. See? That's it. Now we'll apply, okay, the Lie derivative on this second order tensor. Okay? This will be the next lecture. Okay? And then a particular case we will apply the Lie derivative. Okay? When you apply derivative on the metric, this is by definition, you set equals 0, we impose equals 0. This is called the Killing equations. See, as you see.